So welcome to this video, first one about multivariate differentiation. So today we're going to start a new chapter, and that is chapter 13, multivariate differentiation. And as mentioned before, we'll start by introducing the idea of reducing a multivariate function to a single line through the variable space, so that we then get a one-dimensional function along that very line. And of course, for one-dimensional functions, we know how to apply differentiation, so we can compute the derivative. And the question is, how far will that approach take us? Now we've tried with continuity already, and we've seen that for continuity, for continuous functions, that approach did not work at all. So the hope here is that this might give a better result with differentiation. It will turn out that this notion of differentiation along a line is somewhat useful, but it is not the whole truth. So we'll need to extend this concept a little more. Still, let us start by introducing these partial derivatives first. So that is section 13.1, partial derivatives. So again, the basic idea is to look at directional sections again. So let us look at directional cross sections of multivariate functions. So again, what we will have is a set X that is contained in R to the n, and a function defined on that set that maps into the real numbers. We will also need a direction, so a direction for the line that we are going to consider, and that will be a vector d, so a direction d in R to the n. We will exclude the zero vector from that, because obviously the zero vector does not give us a useful direction. We don't just want a point, but we want a direction. And also we need a point, x star somewhere in X. And we'll be a little more specific about this. We want a point that is somewhere in the interior of X. The reason for that is we want to consider a line that goes through this point X star, where at least part of that line around X star still lies inside of X. So we want an interior point because we want to be able to move in both directions from that point. Okay, and now we're going to consider a function we'll call that fd, defined on the reals, or maybe just an interval, maybe just part of the reals, that is defined as fd of lambda equals f of x star plus lambda d. So this part here, x star plus lambda d, that means we're moving along a line through x star in the direction. And we just consider the function f along this line, and that's precisely what the function fd does. It restricts f to this very line. In particular, of course, we can use the coordinate axis as direction. So we can move in x1 direction, in x2 direction, x3 direction, and so on, depending on how many coordinates we have. And we call the functions that we create this way, we call those partial functions. In particular, we can choose the coordinate axis as directions, and we call the result of those partial functions. So we define a partial function fi of lambda as f of x star plus lambda ei. And the question is, of course, what can these partial functions tell us about the properties of the original function f? In particular, with respect to differentiation. So the question is, what can we learn from the partial functions? Now, before we define this notion a little more precisely, before we go into the details, let us first consider a small example. We'll have a look at a function that is defined on R2 and maps to the real numbers. And we will define that function as f of x1, x2 is 1 minus x1 squared minus x2 squared plus 3 x1, x2. Now, let us first see what we get by restricting this function to the lines that are created by the axis, so x1 and x2. And we'll always consider lines that go through the origin. So x star will always be the origin here. So in the first example, we consider directions E1 and E2. Meaning we get f1, the first partial function of lambda. That is then f of the origin plus lambda times the vector 1, 0. Or f of lambda and 0. And that is 1 minus lambda squared. And the other terms all become 0. And of course, we can do the same thing for the second partial function, f2 of lambda. That is, again, 0, 0 plus lambda times 0, 1. So this time we have f of 0 and lambda. And again, this yields 1 minus lambda squared. All the rest becomes 0. So what we can see from this already is both of these terms are less or equal to 1 at all times. So 1 is obviously a maximum, and that is assumed for lambda equals 0. So precisely when we are at the point x star, at the point 0, 0. So that means along the two axes, x1, x2, the function f attains a maximum at x star equals the origin. Now let us try looking at some other direction for that same function. So that's part 2 of our example. We'll now consider a line that is directly in the middle of what we did so far. So now consider the direction d equals 1, 1. If we look at fd, so the function along that line, then we get f of 0, 0 plus lambda times 1, 1, or in other words, f of lambda and lambda. Now f of lambda and lambda, that is 1 minus lambda squared plus 3 times lambda. So what we get is 1 plus lambda squared. And obviously this is greater or equal to 1. Again, the value 1 is assumed at the origin. So in contrast to what we've just seen before, this function now has a local minimum at 0. So f attains a minimum at x star along the line 0, 0 plus r times 1, 1. So what you can see is this gives us conflicting results here. So at least as far as optimization is concerned, where we want to know about minima and maxima, maybe this one-dimensional concept is not quite sufficient. Okay, so as with continuity, our first conclusion is this one-dimensional concept might not quite be the end of the line. So the one-dimensional concept is not sufficient to capture all characteristics of a multivariate function. Still, it will turn out that this concept has some merits. It will actually be pretty valuable, but we'll have to find an extended version and then connect that to these one-dimensional ideas to see how that really works. Before we dive deeper into that, let us first give a precise definition of what differentiation means in this restricted context with the one-dimensional functions. Meaning we will now define the concept of partial differentiation. So this is going to be a very, very important definition. Again, we'll start with a set x, so let x be a subset of R to the n. We usually want an open set here to make things easier, but at least we need an interior point where to apply the differentiation, simply so that we can move in all directions with our lines later on. Okay, so let x be in Rn, f a function defined on x that maps to the reals, and let x star be in the interior of x. Then we first define what it means to obtain a partial derivative. So the function f is called partially differentiable the point x star with respect to xi, or the ith direction, if the function g, we'll define the new function from R to R, defined by g of lambda equals f of x star plus lambda times ei, the unit direction I, so moving in the xi direction. And you can write this more explicitly here. So this is the function f evaluated at x1 star, x2 star, and so on, up to I minus 1. Then for xi, we add this lambda here. And then again, we just copy the point x star. Yeah, so we'll evaluate f at that point for every possible lambda. If that function is differentiable at lambda equals 0. Just as a remark, it is of course sufficient if g is only defined on a neighborhood of 0. You don't need to have it defined on R in total. Okay, it is sufficient if g is defined on some neighborhood of lambda equals 0. And that should always be the case because we explicitly wanted x star to be an interior point. So there is some neighborhood around x star in all directions that is still included in the set x. Okay, so if that function is differentiable, then we will call the derivative of g at the point 0. We'll call that the ith partial derivative of x at of f at x star. Okay, in that case, g prime of 0 is called the ith partial derivative of f at x star. Denoted by, so the notation here is this g prime of 0 is usually denoted as d over dxi f at x star, or sometimes df dxi at x star, or just d subscript xi f of x star, or even more simple, d subscript I f of x star. And we're using this this strange d notation here. It's just pronounced d to mark this as a partial derivative in contrast to a regular derivative. Okay, so that's the ith partial derivative. And of course, we usually be interested in all partial derivatives. So that's the second part of the definition, part 2. The function is called partially differentiable if all partial derivatives exist. Function f is called partially differentiable at x star if all partial derivatives, so starting at df dx1 at x star up to df dxn at x star, if all these partial derivatives exist. Again, we have a notation for that. If these partial derivatives all exist, then we just collect them in one large vector, and we call that vector the gradient of f. And the notation for that is either gradient of f at x star, or this symbol here, a delta that it's tilted upside down. That's called a nabla operator. So nabla f of x star. And that is simply the vector that consists of all these partial derivatives from 1 to n. Okay, so this is called the gradient, and this is called the nabla operator. This is called the gradient of f at x star. Okay, and of course if we can apply a partial derivative once, then we can also apply it twice and maybe 3 times and more often. So higher order partial derivatives are also defined, and they're just defined by repeating that application of partial derivatives. So higher order partial derivatives are defined by repeating the process. So for example, a second order partial derivative, d squared f, and now you have to define which variables you mean here. Usually you just write those as dxi dxj at x star. So what that means is we will first take the partial derivative of f with respect to the rightmost variable, dxj. This is a function defined on r to the n that yields values in r, so we can again apply partial differentiation. And then we just differentiate that one once more with respect to xi this time. And we'll evaluate all that at x star. Okay, so that's a second order partial derivative. And of course, you can repeat the process for third order, fourth order, and so on and so on. And finally, because second order is so common and so important, it gets a name of its own. And we'll often have a look at all partial derivatives of second order. So we'll give those a name as well, and that is called the Hessian or the Hesse matrix of a function. So in particular, the matrix of second order partial derivatives, that is denoted by HF of x star, or sometimes nabla squared f of x star, and that just consists of all partial derivatives of second order d squared f dxi dxj evaluated at the point x star for I and j from 1 to n. And this matrix is called Hesse matrix or Hessian of f at the point x star. Okay, so this concludes this long but important definition. We'll see a few examples in the next video where you can see how to actually compute these partial derivatives.